So in year two differentiation, we learn about the chain rule, and in year two integration, we have the reverse chain rule, which, as you might expect, is the opposite. So here's an example of when we need to use it, where we have to integrate cos of x sin x cubed, like this here. Now, normally there are two clues for when we need to use the reverse chain rule. The first clue is if we have a power or a fraction present. And you can see for this integral here, we have this power of 3 present here, like this. So we can tick off this clue. This power of 3 is a suggestion that we need to use the reverse chain rule. And the second clue is that the other function present is the function inside the power or the fraction differentiated. So what this means is, so we have this power of 3 here, and the function inside the power or the fraction is this sin x here. It's inside the power of 3, like this. And if you differentiate sin of x, you get cos of x, and you can see that we have cos of x present here as well. So that is what this second clue means, is the function inside the power or the fraction, so in this case the power of 3, so the sin x like this. If you differentiate it, which is cos of x, you can see you have cos of x present here as well. So therefore we have both clues present here, so this is suggesting that we can use the reverse chain rule to integrate this. So what do we actually do? Well, you see this sin x to the power of 3 here, okay? What we're going to do is we're going to consider sin to the power of 4x, like this here. So we're going to go up a power from the power of 3 to the power of 4, and you'll see in a moment why we're going to do this. And what we're going to do is we're going to differentiate this sin x to the power of 4, like this here. Now, to differentiate this, we need to use the chain rule. Now, go back to the video on the chain rule that I made in year 2 differentiation if you need a reminder of how it works. The way that I taught the chain rule and the way that I do it is that the chain rule is the inner function differentiated multiplied by the outer function differentiated. So if you consider this sin x to the power of 4, I'm going to write it like this here, where I've put kind of sin x and then brackets to the power of 4. It's the same thing, it's just easier to understand what I mean if you do it like this. The inner function here, the inner function is this sin x here. This is the inner function, and the outer function is this power of 4, like this here. And the chain rule is the inner function differentiated, so the inner function is this sin x here, so it's going to be sin x differentiated, and when you differentiate sin of x, you get cos of x, and then this is multiplied by the outer function differentiated, so this is going to be this power of 4 differentiated. And when you differentiate a power of 4, remember the 4 comes down as a coefficient like this here, and then when we differentiate the outer function, I talked about this in the chain rule video, we keep this sin x the same. We kind of just ignore it and don't touch it, so we still just kind of write this as sin x like this here. We kind of don't really touch it, and then this power of 4 here, when you differentiate a power of 4, it's going to go down to a power of 3 like this here, and then therefore we can simplify this because we can move this cos x inside like this here, and we can write this as 4 cos of x and then sin x to the power of 3 like this here. So this is what happens when you differentiate sin x to the power of 4. Okay, so what we've done here is we've differentiated sin to the power of 4x to 4 cos x sin to the power of 3x. And something we've talked about already in year 2 integration is that integration and differentiation are the opposite of each other. So if we integrate this 4 cos x sin cubed x, it will bring us back to this sin to the power of 4x. Integration and differentiation essentially work like a cycle. And what's useful about this is very close to the question that we actually have to answer. We need to integrate cos x sin cubed x, and here we've integrated 4 cos x sin cubed x. The only difference is this 4 here, and we need to get rid of this. So with this diagram here, what we're going to do is we're going to divide everything by 4. So on this side we're going to get rid of this 4 here, so it's just this cos x sin cubed x, which is what's required, and if you integrate this, this is equal to 1 over 4 sin to the power of 4x. So therefore this is the answer. When you integrate cos x sin to the power of 3x is equal to a quarter sin to the power of 4x, and then remember the plus c on the end. Now when you're doing a question like this, you don't need to do kind of this diagram here, this long diagram. I just wanted to show you how it works. What you have to do is this here is the answer, this sin to the power of 4x, but you also need to divide by the coefficient here, so the 4 in this case, so it becomes a quarter sin to the power of 4x, okay? And that's how the reverse chain rule works, okay? So firstly, see if these two clues here are present, and then if it's a power, so we have this sin to the power of 3x here, increase the power by 1 to sin to the power of 4x, differentiate this to make sure that this form here is the same as this form, and if it's the case, then this here is the answer, but you also need to divide by this coefficient here. Okay, so here's another example where we need to integrate sec to the power of 2x and then tan to the power of 5x. So let's consider the two clues to see if we need to use the reverse chain rule. The first clue is if there's a power or a fraction present. This one's a bit weird because we actually have two powers present. We have this power of 5 here, but we also have this power of 2 here. Let's focus on this power of 5 here, and it will be clear in a moment why we also have this power of 2 here. But let's focus on this power of 5, and therefore we have this first condition satisfied. And then for the second condition, we need the other function to be the function inside the power or the fraction differentiated. So if we have this power of 5 here, the function inside this power of 5 is the tan x, and when you differentiate tan of x, we talked about this in year 2 differentiation, you get sec squared of x. This is actually also given to you in the formula booklet, so you have access to it in the exam. And this is why we have this power of 2 here present as well, because when we differentiate tan of x, we get this sec squared of x, so this power of 2 is kind of here naturally. But this second condition is satisfied because when you differentiate tan of x, you get sec squared of x, and it's present here. So this is a clue that we need to use the reverse chain rule. So let's do that. So we have this tan to the power of 5x, so let's consider tan to the power of 6x. So let's differentiate tan to the power of 6x, so we have to use the chain rule. Remember, the chain rule is the inner function differentiated multiplied by the outer function differentiated. So if we look at it like this here, again I've brought this power of 6 outside to a bracket here like this, but it's still the exact same thing. This tan of x is the inner function, and this power of 6 is the outer function. So the chain rule is the inner function differentiated, which is this tan x differentiated. We've already talked about the fact that when you differentiate tan of x, you get sec squared of x. And then we're going to multiply this by the outer function differentiated, which is this power of 6 here. So when you differentiate the power of 6, the 6 comes down as a coefficient. Remember, this tan of x is going to remain the same. We don't touch it, so it's still going to be tan of x, and now it's going to be to the power of, instead of 6, it's going to go down 1, so it's going to be to the power of 5, like this here. We can simplify this to this here with this 6, this sec squared of x, and this tan to the power of 5x. And we can see that we have the same format here, the sec squared of x tan to the power of 5x, and the sec squared of x tan to the power of 5x. So this suggests that this tan to the power of 6x is the correct format. So this is going to be the answer, but remember, we need to divide it by this coefficient here, this 6. So therefore the final answer is going to be 1 over 6 tan to the power of 6x plus c. Okay, so here's another example where we need to integrate 4x x squared plus 1 to the power of 7. Now this 4 here, what we can do is we can take it out of the integral like this here, so we're left with 4 and then this integral here, so we can kind of ignore this 4 for now and then just multiply it by everything at the end. So we need to integrate x and then x squared plus 1 to the power of 7. So let's consider the two clues to see if we can use the reverse chain rule. So the first clue is if there's a power or a fraction present, and we can see that we have this power of 7 present. I know we have this power of 2 present here as well, but that's not really what this clue means. The clue kind of means as if we have a power of a trigonometric function, or we have like a power of a bracket. It doesn't mean something as simple as like x squared, for example. We need something like this power of 7 here of a bracket. But as we have this power of 7, therefore this clue is satisfied. And the second clue, where the other function is the function inside the power differentiated, well, this power of 7 here, the function inside this power is this bracket this x squared plus 1. So if we differentiate this x squared plus 1, well, if you differentiate plus 1, it's just a constant, so it goes away. And if you differentiate x squared, it becomes 2x. Now, we don't really worry about this coefficient in front of the x, this 2, it isn't really too important. What we need is this x here, and you can see that we have this x here, so therefore this second condition is satisfied, that we have this other function is the function inside the power differentiated, so therefore we can use the reverse chain rule. Okay, so we have this x squared plus 1 to the power of 7, so let's consider x squared plus 1 to the power of 8, and let's differentiate this x squared plus 1 to the power of 8. So we need to use the chain rule, and the chain rule here, the inner function is going to be this x squared plus 1, and the outer function is going to be this power of 8 here. So if we differentiate this using the chain rule, it's going to be the inner function differentiated, so this x squared plus 1 differentiated, and if you differentiate x squared plus 1, as we already did, this plus 1 goes away, and x squared differentiated is 2x, and then this is going to be multiplied by the outer function differentiated, which is this power of 8 differentiated. If you differentiate the power of 8, this 8 comes down like this here, and then this x squared plus 1 is still going to be like this, so we just keep it as x squared plus 1, we kind of just ignore it. And then this power of 8, if you differentiate it, is now going to be to the power of 7, like this here. If you simplify this, 2 times 8 is equal to 16, so it's going to be 16x, then x squared plus 1 to the power of 7. And you can see that we have this x squared plus 1 to the power of 7, which is what we need. So therefore, when we integrate this, it's going to be x squared plus 1 to the power of 8. But remember to divide it by this 16 here. So therefore, it's going to be 4, because remember, we have this 4 at the start here, 4 multiplied by this 1 over 16 x squared plus 1 to the power of 8, and remember this plus c here, and we can simplify this because we've got this 4 times 1 over 16, so this will cancel down to 1 over 4, so it's going to be 1 over 4 x squared plus 1 to the power of 8 plus c. Okay, so here's another example where we need to integrate minus x squared and then the square root of x cubed minus 1. Now, whenever you have an example like this of a square root, you should always use the indices law and convert this into the power of a half, like I've done here. So it becomes x cubed minus 1 to the power of a half rather than this square root here. And I've also taken the minus coefficient out of the integral here like this, and we'll just multiply it at the end. So we need to integrate x squared and then x cubed minus 1 to the power of a half. So let's look at the two clues and see if we have them. Firstly, we need a power or a fraction present, and you can see that we have this power of a half up here, so we can tick this off. And the second clue, where we need the other function present to be the function inside the power differentiator. So the power is this half here, so the function inside the power is this x cubed minus 1. And if you differentiate this, this minus 1 just goes away, and if you differentiate x to the power of 3, it becomes 3x squared like this. Again, the 3 isn't too important, we just need this x squared. You can see we have the x squared here, so therefore this second clue is satisfied, so therefore we can use the reverse chain rule. So if we consider this x cubed minus 1 to the power of a half, let's now consider x cubed minus 1 to the power of 3 over 2. So we've increased this power by 1. And then let's differentiate this x cubed minus 1 to the power of 3 over 2. So we need to use the chain rule. And if we look at this, the inner function is this x cubed minus 1, and the outer function is this power of 3 over 2. So the chain rule is the inner function differentiated, which is going to be this x cubed minus 1 differentiated. And we've already done this. This minus 1 just goes away, and x cubed differentiated is 3x squared, and this is multiplied by the outer function differentiated, which is this power of 3 over 2. So if you differentiate the power of 3 over 2, this 3 over 2 is going to come down as the coefficient. Again, we just write the x cubed minus 1, we don't touch it. And it's now going to be to the power of 3 over 2 minus 1, so it's now going to be to the power of a half. And we can simplify this because 3 times 3 here is 9. It's going to be 9 over 2 x squared. x cubed minus 1 to the power of a half. And you can see we have this x squared, x cubed minus 1 to the power of a half, which is what we need here. So therefore this is the correct form here. So this is going to be the answer, but we need to divide it by this coefficient here. So we need to divide it by this 9 over 2. Remember, when you divide a fraction, it flips. So it's now going to be 2 over 9, and then it's going to be this x cubed minus 1 to the power of 3 over 2. Remember, we have this minus here because we had this minus here at the start that we took out, and then remember this plus c on the end. Okay, so here's a bit of a different example where we need to integrate 2x over x squared plus 5. And as we have this 2 here, we can take this out of the integral. So it can be 2 and then the integral of x over x squared plus 5, like this here. Okay, so can we integrate this using the reverse chain rule? Well, let's consider the two clues. So all of the examples that we've done so far have involved powers, but this one doesn't involve a power. This one involves a fraction because we've got this x over x squared plus 5. So we have the first condition satisfied because we have this fraction here. And then for the second clue, the other function present is the function inside the fraction differentiated. So when we say inside the fraction, what we mean is inside the denominator. So we're talking about inside the denominator, so we're talking about this x squared plus 5. And this differentiated is the other function present in the integral. So if we differentiate this x squared plus 5, this plus 5 will just go away because it's a constant. And if we differentiate this x squared, it's going to be 2x. Again, the 2 isn't too important, the coefficient, we're just focused on this x here. And you can see that we have this x here in the numerator. We have this x, so therefore this condition is satisfied, as with this x squared plus 5 differentiated is this x here. So therefore we can use the reverse chain rule for this integral. Now the question is, how do we use the reverse chain rule? Because before, the way we did it is we kind of increased the power and then we differentiated that, but we can't really do this here for this fraction. We have to do it a different way, and the way that we do it is by considering the integral that we've already talked about a lot in this chapter already, is the integral of 1 over x is equal to the natural log of x, or specifically the modulus of the natural log of x. And hopefully you can see the similarities between this and this, because we've got this 1 over x here, we've got this fraction, and we've also got this fraction here. The difference is here we've got an x, but here we've got an x squared plus 5. So what we're going to do, rather than considering the natural log of x, what we're going to do, because we've got this x squared plus 5 here instead, we're going to consider the natural log of x squared plus 5. So we've replaced this x with the x squared plus 5. So the natural log of the modulus of the x squared plus 5. And let's differentiate the natural log of this x squared plus 5. So to differentiate this, we need to use the chain rule again. And if we consider this function, the inner function is this x squared plus 5, and the outer function is this natural log. So the chain rule is the inner function differentiated, which is this x squared plus 5 differentiated. We've already done it. When you differentiate this plus 5, it just goes away. And when you differentiate x squared, it's 2x. And then this is multiplied by the outer function differentiated, which is going to be this natural log differentiated. And we talked about in year 2 differentiation that when you differentiate a natural log, it becomes 1 over x. Remember, it's the opposite of integration, so we're going to be going back this way. So it's going to be 1 over x, but remember we have this x squared plus 5 present with that we kind of keep constant, we don't touch it. So rather than being 1 over x like this here with the natural log of x, it's going to be 1 over x squared plus 5 like this here. So we differentiate the outer function to get 1 over x squared plus 5. And we can simplify this because the 2x can go into the numerator, so it becomes 2x over x squared plus 5. And you can see that we have this x over x squared plus 5 format that we need for the integral. We have this x over x squared plus 5. So therefore this natural log of x squared plus 5 is the right integral, and it's the correct answer. So that's what we're going to use, except remember that we need to divide it by the coefficient here, and we have a coefficient of 2 here. So therefore it's going to be half natural log of x squared plus 5. That's the integral here. Remember that we actually took out a 2 at the start as well, so if we multiply this 2 by the half, these two are actually going to cancel out, so we're just left with the natural log of the modulus of x squared plus 5. Remember the plus c on the end. So that's how you do it when you have a fraction involved instead of a power. You always consider a natural log of whatever is in the denominator here. So here the denominator was x squared plus 5. So you consider differentiating the natural log of x squared plus 5 like you do here. And for this one you get the natural log of x squared plus 5. Okay, so here's another example where we need to integrate sin of 2x over 3 cos of 2x minus 5. So let's look at the two clues to see if we use the reverse chain rule. So we have a fraction present with this denominator here, so therefore this is the first clue ticked off. And for the second clue, so the function inside the fraction, which is the denominator, is this 3 cos of 2x minus 5. So if we differentiate this, this minus 5 will just go away, so it's a constant. And if we look at this 3 cos of 2x, it's going to be 3 multiplied by, and then we differentiate the cos of 2x. Remember, when you differentiate cos, it becomes minus sin, and this 2 here is going to go to the front. You can go back to year 2 differentiation if you need a reminder. So this is going to be minus 2 sin of 2x, and then this 3 is going to multiply this minus 2 to be minus 6 sin of 2x like this here. Again, the minus 6 doesn't actually matter too much. We just need this sin of 2x, and you can see that we have this in the numerator. So therefore we have this second clue as well. So therefore we can use the reverse chain rule. So as I said before, we always consider the natural log of whatever is in the denominator here. So we have this 3 cos of 2x minus 5. So it's going to be the natural log of 3 cos of 2x minus 5 like this here. So if we differentiate this function here, so we're going to use the chain rule again, and the inner function is this 3 cos of 2x minus 5 here. The outer function is this natural log. So the chain rule is the inner function differentiated, so it's going to be this 3 cos of 2x minus 5 differentiated, and we actually already did this up here. This minus 5 will go away, and this 3 cos of 2x is this minus 6 sin of 2x, and then this is going to be multiplied by the outer function differentiated, so this natural log differentiated, so it's going to be 1 over, and then it's going to be over this here, because remember we keep this the same, so it's going to be 1 over 3 cos of 2x minus 5, and then we can simplify this by putting this in the numerator. So it's going to be minus 6 sin of 2x over 3 cos of 2x minus 5, and hopefully you can see we have this sin of 2x over 3 cos of 2x minus 5, which is what's required for the integral, but we have this minus 6 in front of it, so remember to divide by this. So the answer is this function here, the natural log of the modulus of 3 cos of 2x minus 5, but remember to divide by the minus 6 here, so it's minus 1 over 6, and then remember the plus c. Okay, so this is a bit of a special example that I want to go through, where we have the integral of x over x squared minus 4 to the power of 2. So let's consider the clues to see if we can use the reverse chain rule. Now, when you look at this, you might be thinking to say for clue 1 that a fraction is present, and then do the thing we did before where we do the natural log of the denominator. But for this one, we're not going to do that. What we're going to say is that a power is present, not a fraction. And the reason is because of this power of 2 here. This is a fraction, but if you try and do it in the way that we've done the past two that were fractions, and we try and do the natural log of the denominator, it won't work because of this power of 2 here. What we need to do instead is we need to rewrite this as the integral of x and then x squared minus 4 to the power of minus 2. Remember your indices law, if you have a power of 2 in the denominator, you can rewrite it as the power of minus 2, and we're going to treat this as a power instead and do it like that. If you do it using the natural log way as a fraction, it won't work. And for the second clue, we need to consider the function inside the power differentiated. So this minus 2 here is the power, so it's going to be this x squared minus 4. So if we differentiate this x squared minus 4, this minus 4 will just go away, and then x squared differentiated is 2x, and we can see that we have this x here like this. So we have both of the clues here, so therefore we're going to use the reverse chain rule. So we're going to do it the way we did before with the powers, where we're going to consider this x squared minus 4 to the power of minus 2, and we're going to increase this power by 1. So we're going to consider x squared minus 4 to the power of minus 1. Be careful with the negative powers. Don't make the mistake of trying to put it to the minus 3. We're increasing it by 1, so it's going to go from minus 2 to minus 1. And we're going to differentiate this x squared minus 4 to the power of minus 1. So we're going to use the chain rule like before, where the inner function is this x squared minus 4 and this outer function is the minus 1. So the chain rule is the inner function differentiated, so this x squared minus 4 differentiated, we already did this minus 4 just goes away, and this x squared becomes 2x, and then this is going to be multiplied by the outer function differentiated, so this power of 1 differentiated, so this power of 1 is going to come down like this here to the coefficient. Remember, this x squared minus 4 just stays the same, and now it's going to be to the power of minus 1 minus 1, which is going to be minus 2, like this here. We can simplify this because we've got this 2 and this minus, so it's going to come minus 2x, x squared minus 4 to the power of minus 2. And you can see that we've got this x squared minus 4 to the power of minus 2 that we need in the integral, so therefore this is the correct thing that we're going to use here for the integral. So it's going to be x squared minus 4 to the power of minus 1, but remember to divide it by this minus 2 coefficient here, so it's going to be minus a half x squared minus 4 to the power of minus 1 plus c, and we can rewrite this because we've got this power of minus 1 here. We can rewrite it as a fraction, which is a bit nicer. We can rewrite it as minus 1 over 2 x squared minus 4 like this, and then the plus c. So just be careful with examples like this. If you see a fraction here but you've got a power of 2 in the denominator, we're not going to do it the fraction way that we've done before with a natural log. We're going to convert it into a power and do it like this. Okay, so I think this is a really interesting one, this integral, and there's kind of a weird way that you have to do it, where we have to integrate sec to the power of 5x and then tan of x. Okay, so let's consider the clues. So we have this power present here, we have this power of 5 here, and then if we consider clue 2, if we differentiate the thing inside the power, so the power here is 5, so the function inside the power is this sec x like this here. If you differentiate sec x, we talked about this in year 2 differentiation, you get sec x tan of x like this here, and you can see this tan of x, we have it in the integral here, so that's good. But one of the weird things with the differential of sec x like this here is there's still sec x in the differential in the answer, and as a result this is going to get quite weird, this integral, in a moment. But let's just presume at the moment that it's fine, and we're going to tick this one off here because we have this tan of x here like this. So we have this sec x to the power of 5, so like we normally do, we're going to go one power up and consider sec x to the power of 6 like this here, and we're going to differentiate this sec x to the power of 6 like this here. So if we do this, we're going to have to use the chain rule, with the inner function being sec x and the outer function being this power of 6. So if we differentiate this, the inner function differentiated is going to be this sec x differentiated, and as I've already mentioned up here, this is going to be sec x tan of x, and then we're going to multiply this by the outer function differentiated, which is this power of 6 differentiated. So this power of 6 is going to come down as the coefficient. Remember, we keep the sec x as it is, and instead of the power of 6, now it's going to be to the power of 5. And if we simplify this 6 is going to come to the front, and we have this tan x here, but we now have this sec x multiplied by this sec x to the power of 5, which is now going to be sec x to the power of 6 like this. So when we differentiate this, it's going to be 6 sec x to the power of 6 tan x. And the problem with this here is this is not what we have in our integral. We have sec to the power of 5x, whereas here we have it to the power of 6. So what that means is that we can't use this. This doesn't work because we don't have the right thing that we need in our integral. This is not the answer here, this sec x to the power of 6. We're not going to use this here. So what do we have to do? Well, this is the weird thing about the sec x, is because when you differentiate it, you have it in the answer. What we're going to do is we're going to instead consider differentiating sec to the power of 5x instead, like this here. So we're going to differentiate sec x to the power of 5 like this. So the inner function is the sec x and the outer function is the power of 5. It's basically the same as before. If you differentiate it, the inner function differentiated is the sec x differentiated, so it's still going to be this sec x tan of x, and then the power of 5, this 5 is going to come down as a coefficient, it's going to be sec x, and then it's going to be to the power of 4 like this here. If we simplify this 5 is a coefficient, then we're going to have sec x multiplied by sec x to the power of 4. This is going to be sec x to the power of 5 like this here. And you can see here that this does work. This is what we've got in our integral. So therefore this sec x to the power of 5 here is the correct answer. Remember to divide it by this coefficient here, which is 5. So therefore our answer is 1 over 5 sec x to the power of 5 plus c. So I think this is a really weird example because the kind of power doesn't actually change. It's still to the power of 5 like this here, due to when you differentiate sec. It's quite weird. Okay, so here's one more example, and this is actually mentioned on the specification, this one, the integral of tan of x, and it's actually given to you in the formula booklet, the integral of tan of x. They tell you it's the natural log of the modulus of sec x, but they don't tell you how to get there. And when you first look at this, the integral of tan of x, it doesn't look like something that can be solved using the reverse chain rule. And the key to this is rewriting the integral of tan of x, rewriting the tan of x as sin x over cos x like this here. And now if we consider the clues, well, if we look at the first one, we have now actually got a fraction present. We've got this sin x over cos x. So we've actually got the first clue satisfied. And if we look at the second clue, the other function present is the function inside the fraction differentiated. So inside the denominator is this cos x. If you differentiate cos x, as we know, you get minus sin x, and sin x is present here. So therefore we've actually got this second clue satisfied as well. So therefore we can use the reverse chain rule in the form of a fraction. So what we're going to consider is the natural log of the denominator here. So we're going to consider the natural log of the modulus of cos x here, and we're going to differentiate this. We're going to differentiate the natural log of cos of x. So we're going to use the chain rule. So the inner function is this cos x and the outer function is this natural log. So if we do this, it's going to be the inner function differentiated, so this cos x differentiated. As we've already mentioned, when you differentiate cos of x, you get minus sin x, remember the sin, the minus at the front, and this is multiplied by the outer function differentiated, which is this natural log differentiated, so it's going to be 1 over, remember we need to keep this cos x here, so it's going to be 1 over cos x like this here. We can simplify this by moving the sin x into the numerator, so it's going to be minus sin x over cos x, and you can see that this is what we're actually looking for in the integral. So this natural log of the modulus of cos x is the correct form of the answer. We have this minus here, so we need to divide it by minus 1, which is the same as timesing it by minus 1. So the answer is minus the natural log of cos of x, and then remember the plus c on the end. We can actually rearrange this because remember, when you have a minus in front of the log, this is the equivalent of a minus 1 coefficient. So we can bring this into the natural log as a power, as the power of minus 1, remember? And the power of minus 1 turns it into a 1 over fraction. So this is going to turn it into the natural log of 1 over cos x, and 1 over cos x is equivalent to sec x. And this is why the formula booklet has it written in this format, because you can also write it as the natural log of sec x, and then remember the plus c on the end. So I think this is quite a nice example, because when you first look at it, it doesn't look like you can use the reverse chain rule on it, but you need to rewrite it as sin x over cos x. Okay, so here are two final questions for you to have a go at that I wrote. So pause the video, have a go, and I'll go through the answers in about 5 seconds. Okay, so for the first one, we have to integrate minus cosec to the power of 7 2x, and then cot of 2x. And I'm going to take this minus outside the integral like this here, so we're just left with this integral here that we have to do. So let's consider the two clues in order to use the reverse chain rule. Firstly, if there's a power or a fraction present, and we can see we have this power of 7 here, so that's the first clue satisfied. And then the second clue is if the other function is the function inside the power differentiated. So the power is 7, so the function inside the power of 7 is this cosec of 2x. And if we differentiate this, so remember back to year 2 differentiation, that when you differentiate cosec, it's equal to minus cosec of x cos of x. So if we're going to differentiate cosec of 2 of x, it will be the exact same, except this 2 will go in front of the differential. So it will be minus 2 cosec of 2x cos of 2 of x, like this here. And you can see that we have this cot of 2 of x here. However, we also have this cosec of 2 of x here as well. So this is similar to the sec tan one that we did before, where because we have this cosec of here, when we consider what we're going to differentiate, we're not going to differentiate like we normally do and do cosec to the power of 8 2x like we normally do, because we have this cosec here already. We're not going to do this. We're going to do cosec to the power of 7 2x, otherwise this won't work. So if we consider cosec to the power of 7 2x, so we differentiate cosec to the power of 7 2x, so we're going to use the chain rule with the inner function being this cosec 2x and the outer function being this power of 7. So the chain rule is the inner function differentiated, which is the cosec of 2 of x differentiated, which we've already shown is equal to this minus 2 cosec of 2x cot of 2x, and this is going to be multiplied by the outer function differentiated, which is this power of 7. So when you differentiate a power of 7, this 7 is going to come down like this. Remember, this cosec of 2x remains constant, so it's still going to be cosec of 2x, but now it's going to be to the power of 6 instead, like this. We can simplify this because minus 2 multiplied by 7 is minus 14, and then cosec of 2 of x multiplied by cosec of 2 of x to the power of 6 is cosec of 2 of x to the power of 7, and we have this cot of 2 of x here, and we can see that we have the correct format here of this cosec to the power of 7 2x cot of 2 of x, so this shows that this here is the correct integral. So this is going to be the answer, but remember to divide by the coefficient here, so it's going to be minus 1 over 14 cosec to the power of 7 2x, but remember that we have this minus up here that we took out at the start, so this whole thing is going to be multiplied by minus 1, so this is going to cancel out with this minus, so we're left with 1 over 14 cosec to the power of 7 2x plus c. And then for question 2, we're given that the integral between 0 and a of 2e to the power of 3x over 2e to the power of 3x plus 5 is equal to the natural log of 3 over 3, and therefore we need to show that a, which is this upper limit here, is equal to the natural log of 2. Now these limits we don't actually need to worry about at the start. The first thing that we need to do is actually integrate this expression here, so that's what we're going to focus with at the start, and I've also taken this 2 out of the integral here and put it at the front, and we'll just multiply everything by it at the start. So we need to integrate this e to the power of 3x over 2e to the power of 3x plus 5. So we need to check for the 2 clues to see if we can use the reverse chain rule. So the first one is that we have a fraction present here. I know we have these powers here as well, but we only do the powers if it's for a trigonometric function or a bracket. We don't do it if it's just for e to the power of something. So we have this fraction here, so that's clue 1 ticked off, and the second clue is if the function inside the denominator of the fraction differentiated is also in the integral. So the denominator is this 2e to the power of 3x plus 5. So if we differentiate this plus 5 will go away, so it's just a constant. And if we differentiate this 2e to the power of 3x, it's going to be 2 multiplied by, and then if we differentiate e to the power of 3x, it's going to be 3 e to the power of 3x like this here, and then 2 times 3 is equal to 6. It's going to be 6e to the power of 3x. Again, at the start the 6 isn't that important, we just need to see this e to the power of 3x, and we can see that it's up here in the numerator, so therefore that's the second clue ticked off as well, that we can use the reverse chain rule. So we're using the reverse chain rule here for fractions. We use the technique of doing the natural log of whatever the denominator is. So let's consider the natural log of the denominator, which is 2e to the power of 3x plus 5, like this here. So we're going to differentiate the natural log of the modulus of 2e to the power of 3x plus 5 like this here. So we're going to use the chain rule where the inner function is this 2e to the power of 3x plus 5 and the outer function is this natural log. So we differentiate this using the chain rule. It's going to be the inner function differentiated, which is this 2e to the power of 3x plus 5 differentiated, which you've actually already done. This plus 5 just goes away, and we show when we differentiate 2e to the power of 3x, we get this 6e to the power of 3x like this here, and then this is going to be multiplied by the outer function differentiated, which is this natural log differentiated. When you differentiate a natural log, it's going to be 1 over, and then remember we keep this constant, so it's going to be 1 over the 2e to the power of 3x plus 5 like this here. And we can simplify this by bringing this 6e to the power of 3x into the numerator. So we get 6e to the power of 3x over 2e to the power of 3x plus 5. And you can see that we have this form that we have in the integral, the e to the power of 3x over 2e to the power of 3x plus 5. So that shows that this here is the correct format and the correct answer. So it's going to be this, the integral, but remember to divide by the coefficient here, which is the 6. So it's going to be 1 over 6, and then the natural log of the modulus of 2e to the power of 3x plus 5. Remember we have this 2 at the front that we took out, so it's going to be 2 times this, and this will cancel out with this 6 to leave 3. So it'll be 1 over 3, the natural log of 2e to the power of 3x plus 5. And then remember the constant of integration here. Okay, so this is the integrated form here. So now we need to sub in the limits of 0 and a. So we sub in a, it's going to be 1 over 3, and then the natural log of 2e to the power of 3a plus 5. And this is going to be minus 1 over 3, the natural log of 2e to the power of 3 times 0 plus 5. And all of this is going to be equal to the natural log of 3. Okay, we can do some simplifying here because you can see that we have a denominator of 3 in all of the terms. So we can multiply everything by 3 here like this, and what we can also do is e to the power of 3 times 0 will be e to the power of 0, which is 1, so it's going to be 2 plus 5, which is 7 like this here. So this here will be the natural log of 7. We can move this minus natural log of 7 onto the other side, so it'll be the natural log of 3 plus the natural log of 7. Remember, when you add two natural logs, you can multiply what's in the log, so it'll be the natural log of 21 like this here. And because we've got natural logs on both sides, we can get rid of it on both sides. So it's 2e to the power of 3a plus 5 is equal to 21. Move the 5 onto the other side, so it's 2e to the power of 3a is equal to 16. Divide both sides by 2, so it's e to the power of 3a plus 8. And then to get this power here as the subject, we can take the natural log of both sides, so it's 3a is equal to the natural log of 8. So that means if we divide both sides by 3, it's going to be a is equal to the natural log of 8 over 3. We need to show that 8 is equal to the natural log of 2, which we can do because remember that 8 is 2 cubed like this here. 8 is 2 cubed, and therefore as we've got 2 to the power of 3 here, we can move this 3 in front of the natural log. So it's 3 and then the natural log of 2 divided by 3, and then we can cancel down these 3's, so we're just left with the natural log of 2. So a is equal to the natural log of 2.